In this video, I want to talk about the last two of the convergence tests that we're going to have for infinite series. This is the ratio test and the root test. The ratio test says this: if you're thinking about some infinite series, calculate the limit as n tends to infinity of the absolute value of the ratio of two consecutive terms of the series, the one with larger index upstairs, the one with lower index downstairs. If that limit exists and is less than 1, then the infinite series converges absolutely. If the limit is bigger than 1, including the case where it diverges to plus infinity, the series diverges. And the one remaining possibility, if the limit actually comes up equal to 1, then we can't draw a conclusion from that, in the sense that there are series for which that happens and the series converges, and there's also series for which this happens where the series diverges. So the limit being 1 doesn't tell you anything. Why is this so? Suppose that the limit that we're calculating exists is some actual number L, and that number is less than 1. That means that L can't be negative, so it's at or to the right of 0, has to be less than 1. After a while, beyond some particular index capital N, all of these numbers, absolute value an plus 1 over an, are close to L. That is to say, after a while, all of those absolute value of fractions are less than R, and R in turn is less than 1. So for n bigger than some particular index, this must be true. And we're thinking about the case where R is less than 1. For any n bigger than this threshold, if you multiply through by absolute value of n, you find out that the absolute of an plus 1 is less than R times absolute value an. And I'm going to keep reminding myself that I'm looking at the case where R is less than 1. I'm going to look at some partial sums, but I'm not going to start with A1. I'm going to start with index capital N, and I'm not actually going to look at the AN numbers. I'm going to look at their absolute values. I want to think about having absolute of AN, absolute AN plus absolute AN plus 1, and so on. Because of the inequality that we've previously mentioned, a number n plus 1 has absolute value that's no bigger than R times a number that should be capital N there. A number n plus 2 has absolute value that's no bigger than R times absolute an plus 1, which in turn had absolute value no bigger than R times absolute value of n. So a number n plus 2 is no bigger than R squared times absolute a number n. And then if you do the same calculation again, you'll find out that the expected result is true. A number capital N plus 3 is no bigger than R cubed times absolute an. And I think it's fairly obvious what the indexing is going to be here. This index is 1 more than capital N, and I have the first power of a sub n. This is 2 more than capital N. I have an R squared, 3 more than capital N, R cubed. If we knew mathematical induction, we could give a rigorous argument that this pattern is going to persist, but I'm just going to say, I think it's fairly obvious. So if I form these partial sums, These are upper bounds for the partial sums starting at capital N of absolute value AN. In a way that's similar to what we did for the integral test, add up all of those inequalities, and you find out that the sum of the absolute values of the original series terms starting at capital N, being absolute values, none of them are negative, so add them together, you can't get a negative answer. On the other hand, these terms are the partial sums for a series that we should recognize. Cube there. The partial sum on the right is a partial sum for a geometric series, and the R is the common ratio back from geometric series. We know that that series converges whenever the absolute value of R is less than 1. R is between 0 and 1, so that's the case. Therefore, we know that the limit of these terms converges. The infinite series based on this partial sum converges. But then the direct comparison test says the sum j equal capital N to infinity, absolute AJ converges. Therefore, the sum j equal 1 to infinity, absolute AJ converges. The reason that's true is this series is the same as this series. If I took this one and set the first capital N minus 1 terms to 0, and as we've seen, altering a finite number of terms doesn't change whether a series converges or not. This statement is the definition of the original infinite series converging absolutely. So, to summarize, if we calculate this limit, it comes up some nice finite number, which is less than 1. I automatically know the sum of the a sub n's converges. Not only does it converges in the nice way, in the absolute way. What if this limit is a real number, but it's bigger than 1? Then the picture that we had before changes a little bit. I'll have 1, and then this limit L is bigger than 1. There's some number R between 1 and L. After a while, all of these absolute AN plus 1 over ANs have to be close to L, which means after a while, these fractions are bigger than R, which is bigger than 1 in this case. If you write down the same kind of argument that we had before, you are led to the conclusion that the sum of the terms that we're really interested in are bigger than the partial sums of this geometric series. And since R is bigger than 1 in this geometric series, this series diverges to infinity. The limit of the partial sums for this series has to be at least as big as that. So that tells me the sum from capital N to infinity of absolute value of a number j diverges. If you want to be a little bit more transparent about it, you can think about what happens to the individual terms. If R is bigger than 1, the individual terms are either R to the j times some fixed indexed A value, or the negative of that. I really should have written capital N there. In either case, this diverges on you. The individual terms do not tend to 0. They actually become very large in absolute value. What if we calculate this limit and it comes up equal to 1? We are out of luck if that happens. By that I mean, if all I know about my series is that this limit comes up 1, I can't draw a conclusion. For example, think of the harmonic series, the sum n equal 1 to infinity, 1 over n. If you calculate this limit, since all of the terms are positive, I can just drop the absolute value. It turns into the limit as n tends to infinity of n over n plus 1, which we know from our previous work to be 1. On the other hand, think of the sum n equal 1 to infinity, 1 over n squared. Calculate the appropriate limit. It comes up also equal to 1. But see, this is bad news. The series in the first calculation diverges. It's a p-series with p equal 1. Or thinking back to our original discussion of series, it's the harmonic series, which we proved kind of by hand diverges. On the other hand, this is a p-series with p equal 2, and we know that series like that converge. So in the first case, the limit came up 1 and the series diverges. In the second case, the limit comes up 1 and the series converges. If all I know is that the limit is 1, it could go either way depending on the series. So based only on that information, I can't say anything about whether the original series converges or not. As another example, I want to think about the sum n equal 1 to infinity, negative 1 raised to the n plus 1 over n factorial. Now, this is an alternating series. The individual terms without the negative ones attached to them are positive and decreasing and approach 0. So the alternating series test tells us the series we're looking at converges. The alternating series test doesn't tell me that it converges absolutely, though. And for that reason, and also as another example, we'll use the ratio test on it. So remember, sequences are functions. This formula means when I plug the number n into a formula, what I do is this. I write down a fraction, and whatever the index is, I take the factorial of it. Upstairs, I'm going to raise negative 1 to a power. The power is going to be 1 more than the index. So a number n plus 1 will be negative 1 raised to a power, but it's not n plus 1, it's 1 more than n plus 1, because n plus 1 is the index. On the bottom, I'm going to take the factorial of something, but it's not n, it's n plus 1. When we write down the limit that we have to calculate, it looks like this. When you divide by a fraction, take the 1 on the bottom, flip it upside down, turn it into multiplication. For clarity, I always like to group similar things together. So I've grouped all the powers of negative 1 together and grouped all the stuff that has the factorials in it together. Inside the absolute value, all but one of the negative ones cancel out, and we'll deal with n factorial over n plus 1 factorial shortly. The absolute value of a product is just the separate absolute values multiplied together. And since absolute value of negative 1 is 1, I'm just going to stop writing the factor of 1 down. N factorial and n plus 1 factorial are positive, so their ratio is positive. So the absolute value is just n factorial over n plus 1 factorial. If you remember, n factorial is n times n minus 1 times n minus 2 and you continue till you get down to 1. N plus 1 factorial is n plus 1 multiplied by the number n times n minus 1 and so on. N plus 1 factorial is n plus 1 multiplied by n factorial. So you can cancel the factors of n factorial out, and then obviously this limit is 0. What does this tell me? If the limit is finite and less than 1, then the series converges absolutely. So this tells me that the series that I started with converges absolutely, which, as a no extra cost thing, tells me that this sum also converges. The last of our major convergence tests is called the root test. This is not commonly as useful as the ratio test, but there are situations where it's very convenient. We're going to be calculating roots of things. If the root index is even, you can calculate any root of that nature. Cube root of -8 is -2, and so on. If the index is even, though, as in a square root or a fourth root, in the real numbers, you can't calculate such a root of a negative number. So to prevent any issues of that type, we'll just take the absolute values of things. This will have the added benefit of making what we want to happen. Calculate the limit as n tends to infinity of the nth root of the absolute value of term number n out of your series. If that limit exists and is less than 1, the original series converges absolutely. It converges in the nice way. If the limit is bigger than 1, including the plus infinity case, the series diverges. And if the limit is 1, you can't draw a conclusion from that. Again, I want to talk a little bit about why this is true. The reasoning is going to be almost the same as for the ratio test, except for the details. Suppose that this limit that we're calculating is some real number L, which is less than 1. We'll draw the usual picture. There's 0, there's 1. L is less than 1, so there's some number R between L and 1. R is strictly less than 1, and all of these root quantities that I'm calculating are certainly no bigger than R. After a while, all of these quantities, which are non-negative, are less than or equal to R. So there is an index capital N, so that if little n is bigger than capital N, this nth root is less than or equal to R. Raise both sides to the n power, and you find out that beyond some specific fixed index, the absolute value of an is less than r to the n, which means if I add up the non-negative terms a capital N out to ak, term by term, each one of these absolute a index numbers is less than r raised to that index. This partial sum is no bigger than r raised to the capital N plus r raised to the capital N plus 1, all the way out to r raised to the k. This is a partial sum for a convergent geometric series. The reason that it converges is r is less than 1. So by the direct comparison test, absolute a capital N plus absolute a n plus 1, and so on, converges. Just like before, this is a partial sum for the sum of the absolute a k numbers. If this converges, then this converges. because I've only altered a finite number of terms from 0 up here to absolute A1 plus absolute A2 down to absolute AN minus 1. So this series converges. That's the definition of the original series converging absolutely. I want to think about the sum n equal 1 to infinity, 1 over n to the n power. The direct comparison test would work pretty easily here. If you tried to use the ratio test, though, things would become very awkward. But it turns out that the root test is easy on this one. Take the individual terms, 1 over n to the n, take the absolute value of that, which does nothing since n to the n is positive anyway. Calculate the principal nth root of that and take the limit as n tends to infinity and see what we get. The reason that the root test is going to work so nicely is this is something raised to the n power. When I take the nth root of the nth power of 1 over n, I just get 1 over n. And that's almost the easiest limit on Earth to figure out. The top is a constant, the bottom tends to infinity. The limit does not approach 0. The limit equals 0. Limit is 0. And that's good news because 0 is less than 1. By the root test, the infinite series that we started with converges absolutely. A much less obvious situation, the sum n equal 1 to infinity, negative 1 raised to the n plus 1 power times the 2n power of the fraction 3n squared plus 5n plus 6 over 8n squared plus 2. If you try to do this with the ratio test, it's very difficult. But if you do the root test, life is easy. Calculate the limit of the nth root of the absolute value of the nth term in the series. The nth root is the same thing as the 1 over n power. And if I have something raised to the 2n power, and then raise that to the 1 over n power, it turns out that that's just the square of whatever I'd been raising to the 2n power originally. So this complicated looking thing simplifies down into this. Now, there's various ways to think about this. Probably the easiest way is the thing I'm taking the limit of is the square of something. It's the limit of 3n squared plus 5n plus 6 over 8n squared plus 2 multiplied by itself. If the individual limits exist, which they do, I can split this up into the product of the limits. We've talked about limits of rational functions like this, so I won't belabor the point. The individual limits here are both equal to 3/8. Multiply those together, 9 over 64, and that's less than 1. That tells me that my original series, not only does it converges absolutely, the strong kind of convergence that will let us rearrange any terms we feel like rearranging. The ratio and root tests are the last basic tests that we're going to have to decide whether or not a series converges or diverges. In what comes ahead, we're going to look at some polynomials in the next discussion, which seems odd because we've spent so much time talking about infinite series, but not to worry, the infinite series will be right back real soon now.